Welcome to my Switching, Routing, and Wireless Essentials course. This should be the CCNA version 7 curriculum. This is the second of 3 courses. Module 10, LAN security concepts. So we're going to be looking at endpoint security, access security, layer 2 security threats, MAC address, and LAN-based attacks. So let's go and jump right on in. Endpoint security, that's going to be things that are attacking the endpoint. And again, because the growth of the internet, those endpoints, that connectivity has actually driven network traffic through the roof. Endpoints could be a computer, could be a phone, could be anything. Well, all of them are susceptible to common types of attacks. These attacks are things like denial of service attack or a data breach. That's where organizations lose their data, or even malware/viruses. Malware can actually do some serious damage. Malware costs, economies billions of dollars a year. So these types of attacks are growing because of, the interconnectivity of all of our end devices. The fact that almost everything now is connected to a network in some form or fashion only actually pushes these types of attacks to grow. So some of our security appliances, things like network access control or AAA servers or Cisco's ICE servers or next generation firewalls and VPNs, all of these things are hardware type devices or systems that are allowing us to be providing protection for that network at the perimeter. But the issue is the perimeter is changing because of cloud-based devices, because of those connectivity in devices. So we have some issues with our traditional protection mechanisms and how they are actually governing the protection of network-based resources. At the end of the day, all of these network devices are about being able to secure the endpoints. And we secure the endpoints through a combination. So that's the thing is, when we talk like onion level protection, we don't have a single layer. We have multiple layers. Here we see things like a VP-enabled router. We see a next generation firewall. We see NAC with AAA and ICE. We see an ESA/WSA, that's email security appliance and web security appliance. We see wireless LAN controllers. We see antiviruses. We may even see a HIP or NIP. HIP is Network Intrusion Prevention System. Our NIPs are network versus host-based. So HIP is host-based. NIP is network-based. We also have IDSs, both network-based and host-based as well. And again, all of these provide the additional layers of protection that our endpoints are going to be needing. And again, endpoints can be a tablet, phone, could be a cellular, a laptop, a computer, a printer, it could be a smart thermostat, a projector, and so much more. So in this chapter, we're looking at some of those security appliances. Here we're going to be looking at an email security appliance. And the nice thing here is when we are looking at email protection, Cisco has their ESAs. It does block known threat attacks. It does provide a certain level of remediation against stealthy malware. Basically, it scans emails as they come in, and if they're suspicious, they can quarantine them. They can disable links in emails. They can block access to certain websites if they are shown to be vulnerable. And the nice thing is you can also set them to do auto encryption, both sending and receiving. Nice thing with that is with almost any major cloud-based email system like Gmail or Office 365, Cisco ESA, the auto encryption, if certain things are found in an email, are commonplace now. So moving on, we have our web security appliance. That allows us to do filtering, looking at web content, looking at URLs, looking at URL content, looking at web pages, looking at file downloads, file categorization. Well, the nice thing is we all do that through our web security appliances. If you're looking at any big business or education institution, there's normally a security appliance there filtering mail or filtering web content, not just email. The nice thing is with our WSAs, it builds into the Cisco product line, so it just integrates a little bit easier. However, this is just one tool that works. There's multiple out there. One nice thing that I did like with the Cisco WSA is it does provide the endpoint protection, the advanced malware protection, the visibility of application and content, and it allows you to tie in certain policies and reporting features into the content as well. So that was all kind of a huge benefit. Moving on is our access control. We've already looked at setting up and generating things with local passwords in previous videos. Here we actually see the SSH functionality. I'm just going to grab my pen. This is plain text. This is SSH. You can see the generation of the RSA key, and we can see the generation of only allowing SSH as a valid input. Keep in mind, this is still login locally. We're not doing a AAA server just yet, but this is an example of how to do logins locally. There are some limitations. For example, the login device is on that local that login content is on that local device. The issue with that is if you got 20 devices, you have to now configure those 20 devices to use that local login. And there isn't really a fallback method if there's an issue. And I have run into this where I set a login local, it was compromised, and I lost access to that device. I had to manually reset it and rebuild it from a backup config. So not having a fallback definitely is a hindrance. That's where our AAA comes into play. This is Authentication, Authorization, and Accounting provides the pillar or the framework of basic access control. That means understanding who is allowed access, authentication. What are they allowed to do, authorization. And what are they doing, accounting. Those are the three main pillars of our access controls. Again, authentication, we could do either local or server-based authentication. If we're doing server-based authentication, it will be things like Radius or TACACS. The nice thing is, both Radius and TACACS do communicate with AAA servers. They provide that communication channel. Almost all Cisco routers and switches that are current do provide some form of server-based AAA, and that functionality is just there. All of them do support local AAA, like a Cisco router or Cisco switch, so kind of just depends on what you're trying to accomplish. However, realistically, server-based is going to be the optimal, with a local being a fallback just in case. Authorization is automatically figuring out what you're allowed to do, so that once you're authenticated, you can be given the rights that you need to do whatever you need to do. Authorization governs what the users can and cannot do after they've been authenticated. Authorization uses a set of attributes that describe the user's access to the network, and these basically are the privileges and restrictions for that user. Accounting, in a nutshell, is it documents everything you do. It ties every single action you do back to your login. That's why those logins should be unique and to the individual, not so much a general admin account, but each admin having their own separate account. That way, you can log back and track back everything that was done back to an individual. 802.1x is one of the primary security standards for port-based access control and authentication. Basically, you want to provide any level of protection on a port or wireless connection, you're using the 802.1x standard. 802.1x has three main components: supplicant, authenticator, and authentication server. Supplicant is basically who's requesting access. The authenticator is going to be the device that controls access, and then it will forward our requests to our authentication. A computer comes online from a physical port. That physical port's connected to a switch. That switch is configured to only allow certain access based off of a username or password, for example. The supplicant provides username and password. The authenticator will grab the username and password, hash them, and forward it to the authentication server. Authentication server will say yes or no, and then respond. With the response, the authenticator will be either accessed or denied, and that permission will be passed down to the supplicant. The supplicant will take that and then either be granted the appropriate level of access. All right, moving on. 10.3, Layer 2 security threats. There are vulnerabilities in all layers of our OSI model. However, normally the initial compromise will be done at Layer 2. Whether it be through frame spoofing or MAC address spoofing or other functionality, our Layer 2 vulnerabilities are probably some of the more common that people will have to interact with. Here we have 6 of the more common: MAC address attacks, VLAN attacks, DHCP attacks, ARP attacks, address spoofing attacks, and STP attacks. These are common types of attacks that are attacking Layer 2. And we actually have videos, or not videos, but we have slides covering each one of these. So, we have things like switch-based attacks and mitigation. So, if our switch is under attack, we can mitigate it 4 different ways. We can do port security. That prevents types of attacks including MAC address flooding attacks and DHCP starvation. DHCP snooping mitigation. That prevents starvation and spoofing DHCP attacks. We have our dynamic ARP inspection, DAI, and that prevents ARP spoofing and ARP poisoning attacks. Doesn't prevent them, but it lessens them. And then we have our IP source guard that prevents MAC address and IP address spoofing based attacks on our LAN. Well, again, these solutions aren't effective if the management protocols are not secure. Then that means looking at higher level protocols, they also have to be secure. Things like SSL, TLS, FTP, VLANs, and again, implementing the appropriate management protections, things like ACLs. All of them provide additional components to layer the levels of protection. I'm going to go back one slide. So we have these 6 common types of attacks: MAC, VLAN, DHCP, ARP, address spoofing, STP attacks. Alright, so let's go and let's talk about our MAC address table based attacks. Alright, so first thing we need to do is we have to understand switch operations. So when a switch receives a frame on an ingress port, it will make the forwarding decisions based off of the MAC address table. It needs to know what port to forward that frame, what port it's going to egress on. So it looks at its MAC address table, and it will make the decision based off of the MAC addresses that are known. If it's not known, then it will send out all ports except for the one that it ingressed in to determine what port is the appropriate MAC address. So I got the hiccups. So what ends up happening is, if there is no protection, we can have a MAC address table flooding. Essentially, the threat actor will run some form of MAC attack, and what that does is it creates the ability to write tons of MAC address tables, or tons of MAC addresses to the MAC address table on the switch. That will take the switch, the MAC address table will overflow and has no idea what it's doing. So the switch will flood all the frames at all the ports, except for the inbound one. The threat actor will capture traffic for all the VLAN traffic, or all the traffic, and allow you to move forward. The traffic is flooded only within the local LAN or the VLAN, so the threat actor can only capture traffic within that local LAN or VLAN. So that's one thing that we have to talk about when we're looking at our VLAN and VLAN protection, which I believe that is coming up. So you'll notice here I said MACAV. That's a type of tool used for attacks. The reason MACAV is so dangerous is it can create a ton of MAC addresses, and it can quickly overflow a switch and actually completely destroy the MAC address table on a switch fairly quickly. It can generate, tens of thousands of MAC addresses, if not more, quickly. So I mean, when you have a limit of like 8,000 MAC addresses and you're forwarding that much, it quickly disappears. Another reason these types of attacks are dangerous is because they don't only affect the local switch, they can also affect any other locally connected devices. Anything that's connected to it, again, it's going to start, the switch will start forwarding all the flooded frames out all of the ports except the ingress port, and so that can cascade to all of the other devices. How do we fix this? Like, how do we make sure this doesn't happen? So we mitigate the types of overflow attacks by implementing basic port security. Basically, if a device shouldn't be on the network, we don't allow it on the network. We can specify the number of source MAC addresses that can be learned on a port. And port security is one of the things that we're going to be bringing up shortly, but that's one layer, or one level of protection that could be added. Now, again, this is not always the best way to mitigate these types of attacks, but this is a common way of mitigating these types of attacks. Moving forward, we have our LAN attacks. So in our Netacad course, you're going to see 4 small videos: VLAN hopping, we have double tagging, we have starvation and spoofing attacks. I aren't going to do videos separate for those, but they actually do provide us a walkthrough on each of those. So first of all, VLAN hopping attack is when you can actually connect your laptop or your device to a switch port. Is that switch port set to access mode? Is it set to a trunk? Is it set to dynamic? Can you establish a trunk to that switch? And if you can, the nice thing is you can do what's called VLAN hopping. You can actually double tag a frame so that it has 2 different VLANs. Cisco used to cover the proprietary dynamic trunking protocol, DTP, while in their CCNA curriculum. So now they're not as much, which is kind of interesting. But DTP is still pretty common out there, so we have to understand that when we are looking at in-devices connecting to our switches, we should be hard-coding those to access level ports, not allowing them to enable trunking. So, how do we double tag a frame to go on a network? So first of all, the threat actor will send a double tagged frame to the switch. The outer header has a VLAN tag. So what will end up happening is the trunk port, assuming it's the same as the native VLAN, the trunk port will actually strip it away and then forward it on. So the frame will arrive on the first switch, which will look at the first 4 bytes of the 802.1 tag. The switch will see the frame is destined for the native VLAN. It will forward it appropriately. However, after the VLAN port strips the VLAN tag away, the frame is not retagged because it's part of the native VLAN. So at this point, the inner VLAN is still intact and wasn't inspected. When it is received by the second switch, there is no acknowledge that it was supposed to be for the native VLAN. So the native VLAN traffic is not tagged by the sending switch as specified by 802.1q. We already knew that. The second switch will only look at the inner 802.1q tag. At the threat actor will insert and see if the frame is destined for that tagged VLAN or not. So the second switch will send the frame to the target VLAN or will flood to it, depending on whether there exists a MAC address table entry for that target or not. So essentially what happened was we put 2 VLANs on. The first VLAN was tied to the native VLAN. The second one was on our target VLAN. And because the first switch seen it as part of the native VLAN, it stripped it away, and it stopped processing the rest of the frame. It just sent it on its way. Well, the receiving switch grabbed it, looked at the frame, realized there was a VLAN there, and then forwarded it appropriately to the second VLAN. So These attacks are typically unidirectional and only work when an attacker is connected to a port residing in the same VLAN as the native VLAN. So there are some issues there. And again, not saying that these are common attacks, just saying that this is an attack that is definitely feasible, especially if misconfiguration is present. So presumably the return traffic will also be permitted, thus giving the attacker the ability to communicate with the device on a normally blocked VLAN. Because again, unless there is a layer 3 device allowing for the communication between the VLANs, this shouldn't be allowed. So VLAN attack mitigation, how can we verify it? First of all, hard code access and trunk ports. Disable auto trunking. Be also sure that the native VLAN is only used for trunk links, not allowing our access ports to connect to it. So our LAN attack, DHCP starvation. We have several types of DHCP attacks that are based off of messages. Normally, we'll be getting DORA, DHCP discovery, offer, request, acknowledgement, D-O-R-A. I can spell. Well, the issue is we can manipulate these messages to do DHCP-based attacks. The two big ones are starvation and spoofing. Starvation basically is you take spoofed MAC addresses and you start requesting addresses. This will gobble up all of the address pool. And so when a legitimate user comes online, they don't have enough addresses to be able to connect to the network because the DHCP pool has already been removed or has already been overextended. The issue is these types of attacks are extremely common because of misconfiguration. Oftentimes, it is because network staff failed to realize the appropriate time for release timers. We, at a local business that I worked with, had our IT set up our wireless network. Even though we only had users come in once a week, we allowed the network to issue them an IP address for 7 days. Well, we had different groups each day coming in, and by the third day, there's no addresses. In reality, all of the addresses that were already issued were for users that were there day 1 and day 2 that didn't need addresses because they weren't returning for another week. So instead of having a 7-day lease time, they should have done a 1-day lease time. That way, there was enough address spaces to go around and they could be reused. But because they didn't do that, we accidentally had a starvation attack due to misconfiguration. Next, we have a spoofing attack. A spoofing attack occurs when there's a rogue DHCP server that sends out wrong data. So this is actually really common, especially in training institutions. When you spin up a server, let's say you're working with server 2016 and you're setting up DHCP. And what ends up happening is, in your test environment, you set up DHCP, but it's attached to the real network, and it starts responding to traffic. It starts responding to DORA requests. Well, the problem with that is, you probably shouldn't be handing out addresses, and you did. So that is why these types of spoofing attacks can occur. Again, intentional versus unintentional. Someone spinning up a DHCP because they're doing it in a class and they forgot to do the wrong NIC or something, that's different than a malicious person doing it. They both lead to start spoofing attacks, but intent actually does matter. So like normal, we have videos looking at explaining what these are, which we've already talked about them in previous videos, and we're going to actually talk about these a little bit more in the coming slides. So an ARP attack, basically it uses ARP and it manipulates the way that it works. And again, if we're using ARP or if we're using the IPv6 neighbor discovery protocol, both again do the same function. Most of this can be mitigated by using dynamic ARP inspection, but these types of attacks do pose the risk of things like a man-in-the-middle based attack and other spoofing based attacks. The issue is these attacks are using legitimate network protocols to actually target the network. So that's where it becomes a little bit more frustrating. So we have things like address spoofing attacks. That's where someone's going to actually spoof a IPv4 address. And then from there, they're trying to do something illegitimate. How do we fix that? We can do IP and MAC address spoofing mitigations using IP source guard, IPSG. Normally at the layer 2, there really are not many security mechanisms for preventing these types of attacks. That's the issue. We have STP attacks, and this is going to be where we can manipulate STP by doing either some form of frame manipulation where we're adjusting priorities or causing reprioritization, the re-election process, changing the root bridges. These types of attacks can be mitigated by implementing BPDU guard on the appropriate access ports. Again, if it's an access port, it should not be receiving any form of BPDU because those should only be coming from other switches. So if it's connected to an end device, we do not want to be able to receive any form of switching updates off of those endpoint only access ports. So the name of the game is pretty much figuring out these types of attacks and find ways to mitigate them. The last one is basic reconnaissance using CDP, because CDP is a very common proprietary to Cisco link layer 2 discovery protocol. When it's enabled, it can learn about linked devices or network-based devices. The nice thing is you can disable CDP by doing no CDP. You can also look at other link layer discovery protocols, LLDPs, because all of this is going to be dealing with if someone's able to gain access to a switch or a switch port, they can start mapping the network based off of those types of attacks. So that is all we had for this chapter. A lot of content, but the nice thing is this was more of an overview of some of the things that we've discussed in previous modules. So we looked at our NIPs, we looked at our HIPs, we looked at our web and email security appliances, we looked at the 802.1 standard a little bit more, we looked at layer 2 attacks, things like port security, DHCP snooping, dynamic ARP inspection, IPSGs. We looked at ways to double tag VLAN or double tag certain types of traffic. We looked at mitigations for techniques for common layer 2 and layer 3 attacks. We looked at ARP-based attacks. We looked at STP-based attacks and basic CDP reconnaissance-based attacks. So that's all I had for this chapter. If you have any questions, please reach out.